Thank you, Ranjini, and I thank the organizers for hosting this wonderful event and asking me to speak. So I, okay. Yeah, while preparing the slides for this talk, I was joking with Francesco, who is the next speaker, that my aim was to make a presentation that would be the introduction to his talk. So I'm going to basically present an overview of sort of various ideas that have been discussed over the years in the context of structural glass transition and structural glasses, and in particular, the connection to spin glass and replica ideas. And so in exchange for my offer to provide a good introduction, I've told Francesco that if any questions about the intricacies of the replica theory of structural glasses comes up, it's over to him. Okay, so here is a brief outline of my talk. I'll first start by saying a little bit about the phenomenology of the structural glass transition, as well as some early ideas about how one attempted to understand them. And then I will speak about this investigation of spin glasses that behave in a way that is reminiscent of the phenomenology of the structural glasses, and the connections that were therefore made between the two, leading to what's commonly called the random first order transition theory of structural glass transitions. And then I'll say a little bit about the replica theory for liquids and glasses, the Franz-Parisi potential, and very briefly the Mezard-Parisi theory. And I'll say a little bit by way of segueing to the next talk about things beyond. Okay, so this is really a very basic introduction. What are glasses? Glasses are substances that are disordered microscopically and are solid, frozen in, jammed, arrested structure or state, and not in equilibrium in general. So the well-known case is the glass in everyday language, which is silica glass, which is an amorphous solid under conditions where the stable state is crystalline, namely quartz. So on the right side of the slide, you have an illustration of a cartoon illustration of a two-dimensional version of silica in the crystalline and amorphous solids. And such structural glasses, such as what is shown here in the amorphous case, arise in a large variety of natural and man-made contexts. Okay. And how one makes glasses is not unique. There's a whole variety of ways in which one could produce an amorphous solid, which is sort of sketched here in a diagram taken from a review of Austin Angel. So the most common one is cooling a liquid down to low temperatures, avoiding crystallization, but by no means this is the only way. And vapor deposition, which is one of the cases that's mentioned here, is in both practical and sort of fundamental ways quite interesting nowadays. Okay, so if one, for the moment, looks at glass formers rather than glasses, the fundamental property of these liquids, typically, or fluids, is that they flow under applied stress, and the manner in which they do at a given stress is characterized by the viscosity, and this viscosity, by common experience, increases as you make a material colder. And in the case of glass formers, they actually rise very rapidly. And very rapidly means faster than an Arrhenius temperature dependence. That means that the log of the viscosity would go as the inverse of the temperature. And most glass formers of interest have a rise of the viscosity that is much faster than Arrhenius. And these temperature dependences, a whole zoo of materials are shown here, which show such super Arrhenius temperature dependence. And such temperature dependences generally are well described, though not uniquely, by something called the Vogel-Fulcher-Thaman relation, which exhibits a temperature T0 at which the viscosities are expected to diverge by extrapolation. However, one of course never gets to that point. When the viscosity reaches about 10 to the 13 poise, liquids stop flowing on experimental timescales, which corresponds to about 100 seconds. And so what one sees in the laboratory is a kinetic phenomenon where materials start to behave like solids because they're being probed on timescales that are much shorter than their structural relaxation times. Not only the viscosity, but other dynamical quantities exhibit similar behavior. Okay. The fact that, in fact, there is no qualitative change in behavior at the laboratory glass transition also means that the property of a glass will depend on the method of preparation. The typical method of preparation one discusses is the cooling rate. So depending on how fast or slowly I cool, one observes some behavior such as shown here, be it in the volume or the enthalpy or other properties, where one has sort of an equilibrium regime where there is some behavior that doesn't depend too much on the cooling rate. But below the laboratory glass transition temperature, there's a departure from this liquid-like behavior with a rapid change or a discontinuity, if you will, of slope, but a continuity of properties. And the point at which this happens is higher if the cooling rate is higher, and vice versa. So unlike the liquid to crystal transition, which is also depicted here, where the properties would exhibit discontinuous change, the glass transition, if one thinks of it as a phase transition, is a continuous one from a thermodynamic perspective. However, real glasses are not in equilibrium, and if one waits longer, sitting at some temperature below the glass transition, one finds that there is a very slow process of time evolution, which is called aging, and there are other names in particular contexts, where one recovers what one might expect by extrapolation to be the equilibrium property of the liquid within limits, because the time scale that one can in fact wait is not unlimited. And so and the response of materials to, as an example shown here, applied step stress, which would then lead to a time-dependent growth in the strain, characterized by this quantity called the compliance, is seen to change to larger values, change to larger timescales the longer one waits. And so the time to reach a certain value of the compliance going from left to right in the bottom right figure is longer and longer, the longer one waits. So there's a dependence on the waiting time of the properties, and this is something that's of great interest. And I won't say more about this. I just wanted to point to it as an interesting part of glass phenomenology. Okay, so if one looks at other thermodynamic properties, such as the heat capacity, this shows near the glass transition a sudden jump. How sharp it is depends on details and depends on also the kind of glass former one is looking at. And but invariably, the heat capacity jumps down rather sharply around the glass transition temperature. Okay. As also shown in these panels, the heat capacity not only jumps down, but is invariably higher in the case of a glass-forming liquid than the corresponding crystal when such a comparison can be made. And this is certainly something that can be done for several low molecular weight glass formers. And the fact that the heat capacity for the liquid is higher than that of the crystal means that if one were to look at the difference in the entropy of the liquid with respect to the crystal, which can be obtained by taking the equation that I've shown on the slide and looking at the corresponding values for the liquid and the crystal with delta Cp being a positive number. The fact that the crystal and the heat capacity is smaller than that of the liquid means that the excess entropy, the difference between the liquid and the crystal entropy, decreases more or less strongly depending on how big the difference in the heat capacity is as one goes to lower temperatures. By extrapolation, this excess entropy appears to vanish at a finite temperature, which would seem paradoxical since we think of a liquid as always having a higher entropy content than the crystal. And this is called the Kauzmann Paradox. And this only arises in reality when the excess entropy measurements one has is extrapolated, because invariably before you reach a point where this excess entropy is vanishing, the glass transition intervenes. So that's the resolution in practice of the Kauzmann paradox. But one can ask the question, if one does in fact continue along this excess entropy curve in equilibrium by waiting longer and longer and longer, what happens eventually? So the resolution in principle that has been offered, and it's sort of a question mark at this stage because other interesting things can happen in between, is that there is some kind of a thermodynamic transition in waiting where the excess entropy vanishes. Okay. Now, of course, we are measuring and tabulating excess entropy, which is the difference in the entropy between two phases. But a liquid that is being cooled does not know about the crystal, otherwise it would crystallize. And therefore, one can ask, what is the physical meaning of this excess entropy? And the idea that has been around is that this somehow corresponds to the multiplicity of distinct structures that a liquid can be in. One can imagine defining a constrained equilibrium property or properties of a liquid where one sort of observes it over vibrational timescales. And the idea is that such short time behavior or properties of a liquid would be very similar to that of the crystal. And therefore, what I'm subtracting out is some kind of a vibrational entropy. And what remains is the entropy that is associated with the different reference configurations that a liquid can, quote unquote, vibrate around. So this idea was picked up very early on, one of the earliest theories of the glass transition by Gibbs and DiMarzio in 1958. They developed a theory where the glass transition is indeed a thermodynamic transition at which the excess entropy, or the configurational entropy, as we more generally call it, vanishes. So you have this continuous transition where the excess entropy will vanish at a finite temperature. And Adam and Gibbs built on this Gibbs-DiMarzio theory, describing the glass transition as an entropy vanishing transition, and made a connection to dynamics, or the slowdown of dynamics that one observes in glass forming liquids. And the basic idea is that you imagine that as I go to lower and lower temperatures, there is a certain size of what are called cooperatively rearranging regions that grows, that becomes bigger and bigger. And the meaning of these cooperatively rearranging regions is that if I were to take any sub volume of that region and constrain the system outside to remain as it was, this sub-volume will not be able to reorganize. So there's a minimum size of participating particles that is necessary in order for relaxation to occur. And so this is sort of the first point in the history of ideas about glassy behavior, where the notion of a relevant size or length scale is introduced. And Adam and Gibbs made the assumption that the probability of rearrangement would somehow depend exponentially simply on the size of these regions. So, and conversely, the typical time necessary for such structural reorganizations will grow exponentially with the size of these regions. Now, given what I said about the CRRs, for short, being sort of the minimum size for structural reorganization to occur, one can also make a plausible assumption, as Adam and Gibbs did, that regardless of what the size is, which varies as a function of temperature, the entropy content of a given CRR remains roughly the same. Therefore, if I look at the total entropy of the system, it's some number that's proportional to the number of CRRs I have. And therefore, it's inversely proportional to the size of the CRRs. And if one puts these two equations together and writes an expression for typical relaxation times, one gets the Adam-Gibbs relation, which says the relaxation times go exponentially as 1 over the configurational entropy. And since the configurational entropy is vanishing as one approaches the ideal glass transition, this would correspond then to a divergence of the relaxation time. But more specifically, it's a very strong divergence of the relaxation time, because if for the sake of simplicity, one says that TSC goes as some T minus T naught, where T naught is the glass transition temperature, you have an exponential 1 over T minus T0 dependence, which is a very strong dependence. And that's indeed the Vogel-Fulcher-Thurman dependence that one does fit a lot of experimental data too. Now, this, in terms of how one understands dynamics close to the glass transition, This remains a prominent idea, and it's found to be a good description of some experimental and simulation data, but there's also evidence to the contrary, and there are several questions about this. I will come back to that in a little bit. Okay, now the other line of sort of qualitative thinking and to some extent quantitative analysis is the idea of an energy landscape. So the intuitive picture is that the disordered liquid structure implies many local energy minima, and at high temperatures, the presence of these local minima do not matter. But lowering the temperature, the local minima sampled get deeper and gets harder to go from one to the other, leading to an increase in relaxation times. And this sort of intuition was the basis of, again, an influential sort of discussion by Goldstein, which has been presented quite nicely in this review by Andrea Cavagna that I mentioned here, that in order to understand the dynamics of supercooled liquids close to the glass transition, one must think in terms of transitions between deep local minima and activated dynamics as a result. So this idea is also something that's been around. And in more recent times, this has been sort of investigated by looking at local potential energy minima, which are called inherent structures introduced by Stillinger and co-workers, and in particular, also in connection with glass formation and transition. Now, if one looks at the inherent structures that are sampled as a function of temperature, one does indeed find that they do get deeper, and this is not surprising. One also observes that in several interesting ways, the sampling of these inherent structures does correlate with dynamics. And exactly how then to relate the two in a rigorous fashion is a different question. So in terms of investigation of dynamics from first principles, a very important step was taken in the mid-80s by several people, Bengzelius, Goetze, Solander, and Leuthauser being the first ones, where they considered a recasting of the microscopic equations of motion for slow degrees of freedom, such as density and momentum modes, into a generalized Langevin equation. This is not their work. I mean, this is something that's standard in the that goes by the name of the Maury-Zwanzig formalism. This can be done, but the separation of slow and fast degrees of freedom is sort of dependent on the system one is looking at. So what mode coupling theory did was to then write down an explicit expression for the memory kernel that appears in these generalized Langevin equations in terms of the correlations or products of the correlations themselves, which leads to coupling of density fluctuations at different wavelengths. And this nonlinear feedback leads to a transition to a non-ergodic phase with a power law divergence of the relaxation times. I've written down the schematic mode coupling theory equation of Leuthauser just for reference. The basic thing to notice is that this is an integral differential equation and the integral involving the memory function has the correlation function themselves and the time derivative. Okay. And what goes into defining the memory kernel, I didn't put this down here, is information about the structure of the liquid. And so with structural input, you have a theory that predicts a transition to a structurally arrested state. However, where such a divergence of relaxation times is made, in practice, one does not see it. One sees a window of temperatures over which the dynamics is obeying the predictions of mode coupling theory in several ways. But as you get close to the divergence temperature, you begin to have increasing deviations, and the relaxation times remain finite. Okay, but what one understands is that the mode coupling theory captures some aspects of structural relaxation slowdown as one goes to low temperatures. Okay. Now, if one were to sort of summarize what one can say in broad terms about the class transition, here are the following things. The idealized class transition, not the laboratory class transition, is a thermodynamically continuous entropy vanishing transition. One has an exponential dependence of relaxation times on the distance to the transition. You have strong protocol dependence above the ideal class transition. One has the expectation that the presence of local energy or free energy minima plays an important role in the dynamics of the liquid phase. And there is an apparent crossover in dynamics at higher temperatures than the expected class transition, as described by the mode coupling theory. There is no quench disorder. And even though in the earlier literature, one did not think in terms of an order parameter to describe the glass transition width, if one were to seek an order parameter to talk about, such as some measure of frozen in density fluctuations in the glass phase, this order parameter, one would conclude, changes discontinuous. And there is no latent heat at the transition. So given the progress in the understanding of spin glass behavior, it is tempting to try and make a connection with behavior in spin glasses. And while there are tempting similarities, however, if the spin glass one is thinking about is something like the Sherrington-Kirkpatrick model that Chandan talked about earlier, with a full replica symmetry breaking spin glass transition, there are key differences because the full RSB glass, spin glass transition exhibits a continuous change in order parameter. And even though there's a slowdown of dynamics, it's a much weaker critical type slowdown, etc. So it doesn't seem like a very useful analogy to seek and exploit. However, something that happened again during the 80s is the investigation of several mean field spin glass and Potts glass models that exhibit some significantly different and simpler spin glass transition, which is instead of being a full replica symmetry breaking transition, is what's called a one-step replica symmetry breaking transition, where the order parameter, which is the overlap that was discussed earlier, changes discontinuous. And there are several models, as I already mentioned, but one popular such model is the so-called p-spin model, which has interactions among groups of p spins. So each term in the interaction Hamiltonian involves the state of p spins and a corresponding strength of interaction, which is a quench random variable. And for p greater than or equal to 3, the nature of the transition changes as compared to p equal to 2. There's a jump in Q at the transition, but no latent heat. This is schematically shown at the bottom of the slide. And the overlap distribution function basically below the transition develops a mode at a finite value of Q, in addition to the one at 0, which is what one has in the paramagnetic phase. And if one looks at this quantity x, which is the integral of Q, P of Q with respect to Q, this shows this step-like behavior. So interestingly, in some of the cases, in addition to this one-step RSB transition, there is at lower temperatures a second transition to within each of the individual states that one gets frozen into at the first transition. And the second transition is a full RSB transition. And this has connection with some of the more recent work in the context of structural glasses, so I thought I'd mention it. Okay, now, the other notable features of this one RSB scenario is if one were to come from below at low temperatures where one has a freezing into one of many possible states, because it's a first order transition, even above the transition, these states persist as metastable states. This is sort of schematically shown here, where on the y-axis, I have free energy of individual states. And on the x-axis is the temperature. So the thick solid line that goes across is the total free energy of the full equilibrium system. And the first point I want to point out is that these individual states continue to exist beyond beyond TC, which is the transition, which I'll describe in a minute. And the second notable feature is that these metastable states are exponentially large in number. So one can actually define an entropy associated with these metastable states called the complexity. But if one looks again at the thick line that I've shown, what happens as I approach the transition temperature TC is that the most likely state that I'm inhabiting is becoming lower and lower in some ordering of the states. Basically, let's say the ordering of the value at 0 temperature. So it's a particular feature of the model for which I'm saying this is that this order is preserved of the free energies of the metastable states. They continue to have the same order as you vary the temperature. And so basically the most probable metastable states that characterize the equilibrium behavior is decreasing, and the complexity that one associates with these different metastable states, ordered according to their, let's say, zero temperature free energy, is an increasing function. And therefore, what one has is the fact that the complexity of the system on the whole is also decreasing as you go to lower temperatures, and it goes to zero at the critical temperature Tc. Okay. However, in addition to this thermodynamic transition temperature Tc, the behavior of these models also exhibits a higher dynamical transition temperature when the equilibrium free energy of the system hits the free energy of the highest of these metastable states. And so now, based on what I've said, all of this begins to sound more and more like structural glasses. And this was indeed noted in a series of papers by Kirkpatrick, Tirumalai, and Wallinis in different combinations. They wrote several papers. And they pointed out that there was a strong analogy between spin or quartz glass models exhibiting 1 RSB transitions and structural glasses. And this, in subsequent literature, has come to be known as the random first order transition. So the analogy here is that the complexity is what I have earlier called the configurational entropy. The Tc is to be associated with the Kauzmann temperature, which is an entropy vanishing transition temperature. And then there is a higher temperature Td. And this Td is related to the transition temperature of mode coupling theory. And indeed, the dynamical equations that one writes for these spin models, which I've written down here just for reference, but I won't discuss it, but they basically have the same structure as mode coupling theory. And this was pointed out in one of those series of papers. And okay, and this is actually written for equilibrium dynamics. The non-equilibrium dynamics is more interesting, which perhaps Jorge Kurchan will talk about. Okay, so far in talking about dynamics, the spin glass dynamics versus the MCT correspondence is one exciting analogy, but as I've already said, this describes only the initial stages of the slowdown of dynamics. And so the question is, what about closer to the thermodynamic transition? From what I've already said, the expectation is that, now talking from the perspective of the spin glass models, that somehow if one were thinking about a non-mean field case, the barriers between these free energy minima would be finite, and otherwise in the mean field case, these are long-lived states, and activated transitions among them will control the dynamics. So this kind of thinking led to something called the mosaic picture, where a homogeneous metastable state becomes unstable with respect to fragmentation on a length scale determined by the free energy drive that is given by the configurational entropy and balanced by the surface tension term that would arise from the mismatch between a new state that you might go to versus what already exists. And so in sort of in a form that's familiar from nucleation theory, one can write free energy cost to forming a domain of a certain size as being given by a free energy lowering where the lowering of the free energy is governed by the configurational entropy times the volume of the region plus an increase in the free energy that arises from the surface tension. And this goes with a surface tension exponent, r to some power theta, and where sigma is now considered as a constant. And in the usual sort of way, one can then ask what is the location and size of the free energy barrier, and the location is given in terms of a certain length, which from the form of the free energy cost for any droplet of a certain size is the configurational entropy to the power of -1 over d minus theta, and the free energy cost would correspondingly be the entropy to the power of minus theta over d minus theta. And if one says that the relaxation time is governed by, I should have put a star on these delta f's in the latter equations, but if one says that the relaxation times are given by a free energy barrier divided by kBt, or if one were to say they're governed by the length scale raised to some power in the exponential with suitable choice of these theta and psi exponents, one recovers a form of the relaxation times dependence on the configurational entropy that looks like the Adam-Gibbs relation. So in particular, if one is looking at the first form, where the relaxation time is given by exponential of delta f star, a theta value of d over 2 would lead to the Adam-Gibbs form. There are other combinations if one plays with both the exponent psi and theta. Okay, now what's the situation with respect to the validity, observed validity of these of this relation? So what has been seen in a variety of computer simulations, typically always carried out at temperatures above the mode coupling Tc or the dynamical transition temperature, is that the Adam-Gibbs relation works rather well. But the problem is it works rather well, and these are two examples from our own work. It works well in a regime where it shouldn't, because from what I said, from Goldstein to the analogies with the mean field p-spin model, etc., this kind of a relationship should be valid at temperatures below this dynamical transition temperature. But one sees it working very well above, not very far above, but above. On the other hand, okay, it's one thing to say that what you observe is not according to theoretical expectations, but it turns out it's also not according to some analyses of experimental data. And in particular, I point out here an analysis by Reichert and Angel, where what this graph shows is the configurational entropy in green squares, which is actually measured through some calorimetric method. But what it is being compared with are these blue circles, which are the entropies that are estimated assuming that the Adam-Gibbs relation is valid from dynamics data. Okay, and one sees indeed that there is this regime where they actually coincide quite well. So this is sort of an indication of the validity of the Adam-Gibbs relation. But at higher temperatures, it doesn't, and it's not indicated on this diagram. But where you begin to fall away, when the two data sets begin to disagree, is around what is called TB in this literature, which is identified with the mode coupling crossover. Okay, so so even experiments seem to suggest that in fact at higher temperatures it shouldn't be valid. But in simulations you see that it's valid in those in those temperatures. Now attempts to evaluate the exponents theta and theta and psi, there is no chi, lead to, this is some work of Kamarota, Cavagna and company, lead to values of d-1 for theta, which is sort of the normal surface exponent that one would expect, and a psi value of 1, which is inconsistent with expectations, but nevertheless recover the Adam-Gibbs relation. On the other hand, some recent work where equilibrium simulations have been done below the mode coupling TC, and dynamical relaxation times have been inferred from extrapolation, seem to suggest that the Adam-Gibbs relation doesn't work so well in simulations. And the colleagues involved with this work, Ozawa and company, also then went back and looked at experimental data, which they show here in the bottom right figure, which seems to suggest that in fact it doesn't work. And there is a counter argument that in fact you shouldn't be looking at molar entropy, but rather entropy per volume, but measuring all the quantities relevant, the relaxation times, the density and calorimetric measurements in the same system seem hard. So the matter is sort of up in the air. Many things to understand better. Okay, I'm sort of running out of time, so let me quickly move on through the rest of what I had to say. So far I've sort of talked about the work looking at spin glass models and the connection made between their behavior and structural glass formers of Kirkpatrick, Tirumala, and Volines and co-workers. And these have been very influential in how people think about the structural glass transition problem. But the specific models and calculations involved haven't been on structural glasses. They have been about spin glass models. So they're not theories of the structural glass transition directly. However, in the same period of time as the work of KTW, there was parallel work by Volines and co-workers by sort of seeking analogy with the density functional theory of crystallization to work out a density functional theory of freezing into aperiodic crystals. And this investigation has also been sort of further carried out by Chandan and Oriol Walsh and also Shankar Das and co-workers. And several things have been looked at, such as the stability of these inhomogeneous solutions, the barriers between minima, etc. And these are sort of motivated by the sort of spin glass lore, but not directly connected to. So, so that next step of trying to work out a theory like that for spin glass models has been carried out since the mid-90s by several people, Parisi prominently, Silvio Franz, Mezard, and so on, Monason. And this work has sort of is ongoing. There's a lot of recent work that has been done that has been summarized in this review that I mentioned at the bottom of the slide, and also a book by Parisi Urbani and Francesco Zamponi called The Theory of Simple Glasses, and so Francesco will talk about these. But just to sort of say, in the next 5 minutes or so, So one of the early works to sort of try to work out.
Srikanth, you have, it's 50 minutes now, so yeah, make it 2 minutes maybe instead of 5 if possible.
Okay, I'll try.
Okay, thank you.
Okay, so one of the sort of initial and appealing ways of trying to do a replica theory is the so-called Franz-Parisi potential. And the basic idea is one considers two copies of a system, and this was done for spin models initially, but later for liquids, where one of the copies acts as sort of an applied field on the other. So in other words, one considers one of those copies to be fixed in some configuration and evaluates an effective potential for the other copy as a function of the overlap between them. So in other words, this is like a Landau free energy with Q as the order parameter, with the configuration of the second, the master copy fixed. And this effective potential can then be averaged over the equilibrium distribution of the second copy. And this can also be done in different ways by applying a pinning field that is proportional to the overlap instead of fixing the overlap to have a certain value when you do this evaluation. But basically what one gets is this Franz-Parisi potential as a function of Q. And as temperature is varied from high to low, the behavior of this function is as shown, where in addition to the minimum at Q equal to 0, a second minimum at finite Q develops, and this corresponds to sort of these two copies of the system sticking close to each other. But that event is less probable as compared to them being completely dissimilar by a cost which is given by the complexity. And therefore, the height of the second minimum at any given temperature is the complexity, and this is a way of measuring it. And when that height goes to 0, as shown in the lowest curve, one reaches the ideal glass transition. And this has been used as a way of introducing self-generated disorder and to evaluate the glass transition. Okay, so here are some results that were obtained by Franz and Parisi and co-workers. I won't go through them, but the calculated effective potential with some gaps, there's some technical reasons for that, looks like what is expected. This was done for a hard sphere fluid using a particular integral equation liquid state scheme. Okay, now this I will completely skip, but just to say Mezard and Parisi in parallel essentially also looked at not considering two copies, but m copies of the liquid, and by steps that I won't describe, in addition to evaluating where the transition was, they also looked at the properties of the glass. Okay. This is sort of the only slide where I can make a direct connection between some things that I've been involved with and this line of work. So you know, I had, through simulations and looking at the inherent structure, thermodynamics, evaluated a glass transition line as a function of density, which very soon after was evaluated through the schemes that, such as what I just mentioned, by Parisi and co-workers, finding basically a fairly good agreement between the glass transition line obtained from dynamics, which in that case agreed also with the thermodynamic evaluation, and from the replica theory. And we carried out some related work later on, we being Ashwin, my student, then Gautam Menon. Okay. This is basically it. I mean, so there are many other related topics that I haven't talked about, with in particular aging dynamics, which I believe will be the topic of Kurchand's talk, and the development of a theory of the glass transition, fluids of hard particles in the limit of infinite spatial dimension, where a lot of things become much clearer, and this is the subject of Francesco's talk next. Okay, so let me stop there, and I would like to extend my congratulations to Giorgio Parisi for the Nobel Prize, of course, but this is also an occasion to acknowledge the kind of inspiring presence he has been for generations of students, collaborations, colleagues worldwide. I personally have been a beneficiary of his sort of very accessible and insightful interactions with him, personality and interactions with him. And I would like to thank Giorgio as well for those on several visits to Rome. And let me stop there.
Thanks, Srikanth, for that very nice overview. I wish we had a little more time. Questions? Professor Morinari, do you have a question?
Yes, maybe.
Yes, please go ahead.
You know, since you are the real glass expert, say, at the end,
First part is
how much do you think is the promise of Giorgio in this field? I mean, will one be able to really lock down things in some sense? Is that a real possibility? Thank you.
I'm sorry, Enzo, say that again. I didn't quite catch.
Yeah, no, I say at the end, right? From an insider, okay, what do you think is the potentiality of replica symmetry breaking and so on in order to really somehow wrap up the field in some sense? It's a bit of a provocative question, but I think it's interesting.
So, like in the spin glass literature, I think the work that Giorgio has been involved in is comparably influential in the context of structural glasses in the mean field regime. Like in spin glasses, there is a lot to do beyond that, and that, you know, also Giorgio has been very involved with. I didn't talk about it, but no, his role in the structural glass literature is, I mean, they're basically sort of very, very broadly, you know, there was this early phase where KTW made tremendous progress, but beyond that, for a lot of the important things that have happened, Giorgio has been centrally important.
Thank you so much.